as you all know, today we are here to have an overview of CFD. Before we begin, I would just like to post one comment. So I think, as Mehul or Aishwarya Shri just mentioned, uh, yes, this is very much helpful for mechanical students, but as you can understand, this is just an overview of CFD. And CFD essentially is a technique. Okay. So, yes, it will be very much helpful for mechanical, but apart from mechanical, these techniques can also be implemented by people from civil, from people from automobile and other stuff. In fact, just to give you a very interesting example, the other day I was sitting with a friend of mine, and he is an expert in animation. And what I saw is even people who build animations, build all these beautiful scenes from Avengers and stuff like that, even they utilize some of the meshing techniques from CFD. So, the possibilities of CFD are essentially limitless. But yeah, so on that note, let's begin. So, as always, it is very much helpful for me if I know who you are, at this juncture itself, so that I can plan the delivery of my webinar accordingly. So I think the first question was already answered. So I think some of you are students, some of you are working professionals. So maybe still, could you please in the comment box put down 1, 2, or 3? So one is if you're starting afresh, two is if you know some CFD, and three is if you're already performing CFD simulations at let's say your institute or wherever you work with, and stuff like that. So guys, one request.
Guys, yeah, Sarang, so guys, the thing is, a lot of answers, you are giving it to me, which is asked by Mr. Sarang, right? So what you have to do is, when you're writing the answer, right? Because in the entire session, it is going to be a kind of an interactive session. So what you have to do is there is a drop down feature, okay, where you can select the name of the person, okay. So there will be three names you will be seeing: Mehul, Sarang, and Aishwarya Sri, okay. So whatever the questions asked by Sarang, you have to reply back to Sarang. Okay. Not to me and Ishwarya Sri, because Mr. Sarang wants the visibility on that. Okay. So I can see Arun, Sudarshan, Rahim, Harim, Mayank, right? Dhawal Chauhan, Gokul Krishnan, Deepak Kumar, okay, Barinidhan, Ashish Ranjan, right? Hasim. So you guys have actually answered me. Okay, you can see wherever you're writing your answer, above that there is a drop down feature, right? Beside two. So you have to click on the drop down feature and select Sarang. Hopefully that is understandable. So still, Sudarshan again. Okay, great. Thanks for confirmation. Brahma Teja, you're answering me. Click on the drop down feature and answer it to Mr. Sarang. Okay. So just to let you guys know about it, so that during the session, whenever the questions are being answered, a question is being asked by Mr. Sarang, you have to answer it to him directly. Okay. Don't answer it to me or Aishwarya Sri. All right.
Thanks, Mehul, for that. And yes, guys, you can answer to me directly, or you can even, put it as a reply to everyone. That's not a problem because, just to get your blood flowing, I'll be asking you a lot of questions. So please be very interactive in the chat box. Thank you. All right.
Thanks,
So
Arun.
yeah, thank you. And next, so to those who, let's say, answered two or three, maybe could you let me know in a yes or no if you know these terms, mesh, boundary conditions, stuff like that, if you have heard about it, or if you know it, say yes. Otherwise, just put a no. Okay, thank you for that. And lastly, if you have any, whenever we attend a webinar, we have some expectations from the webinar that, okay, what I'm going to learn this today, or, this is what I'm more curious today. So is there something specific that you're looking for in this webinar? If so, please put it down in the chat box. I'll give you another 30 seconds. If not, we'll just move ahead. All right, so seems that we don't have much expectations, so that's good and bad. All right. Next, just a quick check. Uh, so uh, I hope my voice is clearly visible. My delivery speed, meaning whatever I speak, you are able to understand. And I think the rest of the concerns are already, taken care of by my colleagues at Skill-Lync. So my mic and my delivery speed, everything is okay, right? You are able to understand and hear me properly. Okay, perfect. Thanks for the feedback, guys. All right, and on this note, let's dive into CFD now. So first, let me explain you what is the scope of this webinar. Because CFD, if you consider this as a topic, as a research area and stuff like that, people have spent their complete lives researching for it. So by lives, I'm essentially going to the time frame of 30 to 50 years. So it is obvious that in this limited duration of, let's say, 1 or 1.5 hours, I won't be able to cover everything of CFD. So what I've planned is I'm going to give you a very brief introduction to CFD, what CFD is all about. I promise no complex equations. In fact, no equations at all. I've tried to stick to that. Third point is my personal favorite. So at the end of the webinar, what I essentially want to achieve is I want to have your admiration about the world of CFD and the possibilities that it holds. So as I mentioned before, some of the techniques of not essentially CFD, but some of the meshing techniques are even used by people in animation. So the possibilities are essentially infinite. And lastly, this is something that comes from the industry. So as you know, whatever product you buy, let's say it's an automobile, or it can be a refrigerator, or it can be anything. So all of these things are tested by companies in their labs. And slowly, what is happening is companies are moving towards the concept of what we call as a virtual release. So what does that mean? It means you recreate the testing environment in a simulation software. You simulate the complete test, and without actually performing any test, you should be able to tell just from the simulations itself whether or not this product passes the quality benchmarks. So this concept of recreating the test environment, this is known as creating a digital twin. Okay. So again, this is also something that I would like to talk about. So I think everything is straightforward here. The scope of the webinar is clear to everyone. Next, let us talk about what is this webinar going to hold for you. Okay. So first, if you imagine that you're going on a journey to any place, let's say, for example, why think small, right? So let's say you're going to the moon. So naturally, you will have some training. You will, read some information that will help you survive in those stringent environmental conditions and stuff like that. So similarly, if you are starting your journey in CFD, you will need some tools or some understanding from whatever you have learned so far in your engineering. Okay, so I will briefly take you through these nuances of your engineering basics. Next, it is also important to understand how CFD was developed over this last decade, not essentially decade, this last century, I would say. So that's the look in history part. On the third bit after the history, this is where I will formally introduce CFD to you. Okay, so as you can understand, unless we complete 1 and 2, speaking about point 3 won't be of much help. Okay, next we will talk about how CFD works. So again, there are some intricacies to be talked about here. And lastly, the applications of CFD. And the sixth bit is, it's a bit of a good surprise that awaits for you at the end of the webinar. So I wouldn't spoil it at this point. Okay, so let's start with, the first bit, which is your engineering past. So I would like to talk about your engineering past on two aspects, or rather three aspects. And first of them is the physics of the matter. Okay, so I think over your 3, 4, 5 years of engineering, you would have heard about different phenomena, different governing equations. You might have even derived some of them. So what are all of these? These are essentially phenomena that are occurring in nature. Some of the scientists have analyzed them and given a mathematical formulation for them. So this mathematical formulation is what you see as governing equations. So for example, on the left, what you have is your Bernoulli's principle. On the right, you have Fourier's law of heat conduction. So, I think you might have equations upon equations for all of these. So this is something that you need to remember when you're talking about CFD. Next, so governing equations will have a lot of variables, and these variables can be flow variables or material properties, or flow properties and stuff like that. So you need to understand all of these quantities as well, because essentially your governing equations are built up of these quantities, and these quantities are how you would relate to the physical phenomena that is happening. Okay, so for example, if a fluid is flowing, you will need to know what is the viscosity of the fluid, you will need to know what is the density, surface tension, blah blah blah. So all of these flow variables will help you interact with the fluid, or the flow, I would say. So that is the physics of the matter. Next, let us talk about, oh, okay, so let's do this small exercise. Okay, and fingers on your screens now. Let's do the small exercise. So just focus on this image on the left, and this is what we are going to do. Let's say you climb up to the top of the building that you're sitting in right now. You have these two bowling balls, both of them of 1 kg each, and you just drop them from the top of the building. So uh, for the first case, I want you to tell me if the both balls will hit the ground at the same time. Will they reach the ground at the same time or different? Just type in same or different. I think it's pretty obvious, but yeah, let's get you started. Come on, guys, this is very obvious. It can't be different. It has to be same. Okay. Okay, that's clear. I think that does not need any explanation. Let's go to case 2 now. Okay, so now for case 2, again, the same exercise. It's the same ball, maybe made up of a different material, hence you have a different density, but the shape and size of the ball is the same. And then you're again dropping these two balls from the top of the building. So now tell me, will both the balls reach the ground at the same time or different? Guys, come on, think about it. Think about, don't just go by, your feel of the things. Think about the mathematics involved. I think this is a very common question asked in the interviews as well. All right, so okay, let's discuss this. Okay, if I tell you that, okay, tell me how much time does this ball take to reach to the ground? How will you calculate that? I think you have learned this in your 11th and 12th. And just to give you a hint, the answer is already there on the screen. I think everyone has heard about these three equations. Maybe I'll open the pointer. Yeah, these three equations, I think everyone knows. Yes, using Newton's equations of motion. That's perfectly okay. Now, if I want to evaluate the time, what you will use is the second equation. So S here will be the height of the building, U initial velocity, T time, A acceleration. Okay, there is no initial velocity, hence the first term is not there. S is the height of the building, right? So S equal to half AT square. If I assume S as 5, that means 2 goes here. So it will be 10 equal to AT square. If I take the value of acceleration as 10, the time essentially happens to be 1 second. Now, if I use this equation for the 1 kg ball or for the 2 kg ball, do you think the time will be different? Yes, no? Good. So obviously there is no mass term in this equation. Hence, the time will be same. So what can we conclude from here? irrespective of what is the mass of the body, the time required for it to fall to the ground is essentially the same, right? So why is this problem presented as an exercise in a CFD webinar? That is the obvious question, right? But the point that I'm trying to make is, guys, you have to be very careful about your understanding of the physics. Why? Because all the CFD softwares that you're going to use in your, let's say, professional field or educational field, they are dumb. Why? Because whatever inputs you give to the software, the output will essentially be the same. So if you give garbage in, it will be garbage out. As simple as that. So in order to distinguish the garbage from the actual result, you will need to have this understanding of basics. And this understanding essentially comes from your engineering. Okay. Now, last question for case 3. Again, same or different? Let's come on, think about it. Okay, that was a trick question, and all of you fell for it. Okay, not all of you. Okay, let's quickly elaborate on this and move forward. So, yes, the answer is right. It is different for sure. But why is it different? Because if you consider the feathers, they are affected by the air resistance. The air resistance will not be as pronounced for these balls as it is for the feathers. But the interesting question now is, the equation is still the same for both the bodies. So which of these quantities is changing for both the bodies? So S is still the same. First term is not there. The A is different for both the bodies. Why is that? Again, I'll repeat my question. The term A in this equation is different for both these bodies. Any idea why? Exactly, guys. Very good. So the difference is because of the air resistance. So the air resistance will be different for the first ball, it will be different for the second ball, and which is why the effective force or effective acceleration on the bodies will be different. Perfect. All right, now let's move ahead. Okay, so that was all about physics. Next, by the way, is it clear for everyone? Do we need to spend any more time on the physics? If it is clear, just type in clear. Perfect. Thank you. Now let's move to the next bit. Okay, there's something very interesting coming up here. So now we have talked about physics, but the physics is nothing if you do not have a mathematical formulation for it, right? So yes, you can say that the apple falls on the ground due to gravity, but if you did not have the Newton's formula, which actually calculates the gravitational acceleration or acceleration provided by any heavy bodies, g m1 m2 upon r square. So if that was not there, you wouldn't be able to let's say quantify the gravity. Hence, physics is you know incomplete if we do not have the mathematics behind it. So what all mathematics from your engineering past will you need? So some of them are solutions to simultaneous equations, your partial and total derivatives. Then I think most of you might have done this control volume based approaches and derivations and stuff like that. Partial differential equations also, I think you might have solved them using complementary functions and particular integrals and stuff like that. Finally, the most important of them all are your numerical methods. So I wouldn't speak in detail about the first four, but is everyone aware what numerical methods mean? So your Newton-Raphson method, your bisection method. So essentially, it is a way of approximating the value by using some numerical techniques without actually solving all the equations. So are numerical methods known to everyone? Yes, no? Perfect, perfect. Thank you, guys. Thank you for being so responsive. All right, so I'm going to do a small demo of numerical methods just to help you understand how they work and which part of it is integral for CFD. Okay, so as a demo, what we are going to consider is something that is known as Taylor series expansion. So what are we trying to achieve? So imagine that you have a function f of x that is continuous for the given domain. What I want to do is I have a number x2. I want to evaluate the value of the function at that number x2. Okay, so what is known to me? I have another number x, and I know the value of the function at x, that is f of x. Okay, and what I also know is, for example, if x2 is 1.1 and x is 1, then I am going to define x2 as 1 plus 0.1. So what I'm trying to say is dx is a small increment from x that will give me x2. Okay, so just to reiterate, I want to evaluate the value of the function at x2. What I know is the value of the function at x. Okay, then the Taylor series expansion says that the value of the function at x2 is equal to value of the function at x plus first derivative at x into dx, second derivative of x into dx square upon 2 factorial, and so on and so forth. Okay, so this is an approximation of the value of the function at x2. Now what I did is I took some common functions, I put them in an Excel table, and I'm going to show you how accurate the expansion looks like. So can I get a quick feedback if the screen is visible? My Excel sheet is visible? Yes, no? Okay, perfect. Thank you, guys. So as you can see on the screen, what I have is I've chosen the function as sine x. Okay. Now here, just to make you aware, I have written the Taylor series expansion of f of x plus dx, which is f of x2, for example. So f of x, that is sine x, plus f dash of x into dx, plus f double dash of x into dx square, and so on and so forth. Okay, so as you all know, Excel has its own built-in library of functions. So in this first column, what you see is the direct value that Excel gives us. So I just type in a formula sine of x, and the value is given here. Now, similarly, on this next column that you have, I have implemented the formula using the Taylor series. So as you can see on your screen here, maybe you will have to zoom in your mobile screens or something like that, but this is the Taylor series formula that I have implemented. Okay, so all these values in this column are the Taylor series value, and these are, let's say, the actual values of the function. So if you compare the left and right columns, what you will notice is we are very close in approximating the value of the function. So the Taylor series value, they are very close to what we have here. But the important thing to remember is the delta that I am using. So if you see in this formula here, my delta or dx is 0.39. So this is essentially pi by 8. So every value is incremented by a value of pi by 8. Okay, so this is clear, I suppose. Maybe I'll ask you, yes, no. Is this clear what I'm trying to convey? Okay. Guys, just in case if my voice is not audible, I suppose my friends at Skill-Lync will let me know. So please check your internet connection or your audio connectivity. Okay. All right. So let's take another example, that is the Taylor series expansion for another function that is x cube. Okay. So again, the same thing. I've written the formula here. I have evaluated the values in this column directly from Excel. And on the right hand side, what you have is the values from the Taylor series. All right. So again, as before, if you compare these two values, we are still in a very close match with the actual value. Okay. And the dx that I'm using here is 0.1. So 1.1 is here. 1.2 essentially is 1.1 plus 0.1. So the dx in this case will be 0.1. Okay. Now, I think I've already highlighted this. So if you see here, the error between these two or the difference between these two is pretty high. So why is that? Let's have a deeper look. So when I evaluated it here for 2.1 for using the Taylor series expansion, what I did is I used the dx as 0.1. What is the meaning of that? I used the value of the function at 2 and I used an increment of 0.1 to estimate the value at 2.1. What is happening in the second case? In the second case, I am defining 2.1 as 1.1 plus 1. So what has changed? The delta that we were using, it changed from 0.1 to 1. And you can see the tremendous impact it has. Okay, so suddenly when our values were matching very close, now we have a very huge difference, right? The error is probably goes close to some 60-70%. Okay, so what is the moral of the story? In order to implement any numerical techniques or any estimations, what you have to understand is the incremental value has to be very, very small. Okay, this is the moral that I wanted to convey. So is it clear for everyone? Yes, no? Okay, fine. So this is done. Let's move to the PPT. Okay, I see there are some people saying explain one more time. So do we need it one more time, guys? Say yes if you want me to explain it again. And guys, I'm here to help you. Okay, so feel free to say that, okay, hey, we need this one more time. It's absolutely okay. No problem. Okay. All right. So, okay, let me go back to the PPT for a minute. Okay, see, the aim of this exercise was to evaluate the value of the function at a value, let's say 1.1. And what are the inputs that we have? We know the value of the function at 1, and we are going to define it as f of 1 plus zero point 0.1, which is a small increment in x. So that is the same thing that I did here. When I am evaluating the value of the function at 1.2, I am using the known value of the function at 1.1 and incrementing it by 0.1. So if I use this small increment of 0.1, my all values are, pretty good match. So if you compare the left and right columns, everything matches very well. But now I get greedy. What I do is, instead of using the value of dx or the increment as 0.1, I say that, okay, let me increase this to 1. What does that mean? I am going to write 2.1 as 1.1 plus 1. Okay. Before, what I was doing is I was writing 2.1 as 2.0 plus 0.1. What does that mean? I'm using the known value at 1.1 in this case and the known value of 2 in this case. And now I'm comparing what is the difference between the outputs. Okay. So what I conclude is, if I use a very high value of dx, then my error in estimating the value of f of x is very high. Okay. So if I do it in terms of percentage, yeah, so I have an error of about 54%. Okay, so the conclusion is my dx has to be reasonably small for all the numerical estimations to work. Is it clear now? Yes, no? So dx in all the previous cases is 0.1. So if I am evaluating at 1.2, it is 1.1 plus 0.1. At 1.3, it is 1.2 plus 0.1, and so on and so forth. Okay, so I hope it is clear now. So guys, this is very important because I'm going to use this as a reference when I talk about CFD. Okay, so I hope it is clear. Let's get back to the PPT. Okay, so the last part about this revision is, well, essentially your common sense. So I know this sounds a bit weird, but as I already explained, softwares essentially are dumb. And one good part is that is why we have our jobs, right? If softwares were able to do everything, well, companies would essentially just spend money on softwares. They wouldn't hire anyone. So good that the softwares are dumb because then we have our jobs. Again, as I mentioned, garbage in, garbage out. That is also very clear to everyone. The third bit is something that I have said. So this is essentially my quote. So, anyone can build and run a CFD simulation. So if you just know which buttons to click, or if you just memorize on the procedure to be followed, anyone, even a 10 standard guy can run a CFD simulation. But the second part of the CFD simulation, that is interpreting the results, this is where a CFD engineer has to play his role. Okay, so it is not that everyone can read the simulation results. If you want to understand the simulation results, you have to be very strong in your fundamentals of physics, mathematics, and the most important bit is your common sense. Okay, and in my honest opinion, engineering is essentially your very elaborate course in common sense. Okay, so this covers the first bit of the webinar. Are there any questions so far, or can we quickly move ahead with the history? So, Trinanjan, sorry if I'm pronouncing it wrong. So, f of x equal to 2.1, or rather 2.1 is equal to 2.1 cube. That's true. But what is this? This is your, implementing the direct formula for f of x. What I'm saying is, you don't know that f of x is equal to x cube. What you only know is f of 2.1 is whatever the value is. F of 2 is 8. You don't know at the moment that f of x is x cube. And this is where Taylor series will help you, or this is where all the numerical estimations will help you. So for Taylor series, 2.1 is 2 plus 0.1, and then the Taylor series formulation. Okay, so can we move ahead? Yes, no? Okay, thank you guys. So in the interest of time, I will quickly walk you through history, but this is not something that you have to memorize or something. It's just for your general understanding. Okay. So if we go a lot of years back, when you had some very rudimentary equations explaining physics. So this was probably the time when, let's say, Apple fell on Newton's head, or that far back. Okay, so at that point you didn't have very elaborate mathematics or elaborate physics, so you had some very rudimentary equations. Then came the advancement in mathematics, especially calculus, and that is when you started getting all these complex governing equations. Now the problem was, you have all these complex governing equations, but are you able to solve them? So some of them yes, some of them no. Then another advancement in mathematics came in, which was your numerical methods. And suddenly all these equations, which were very difficult to solve, you were still able to solve them in a different way. So as I explained, let's say you did not know that this f of x is equal to x cube. You are still able to find the values at different locations simply by using your numerical techniques. Now, numerical solutions were now available for complex mathematical operations, but there was another problem, that these mathematical tools that we were using, they require a lot of manual efforts. So all these solutions that you had, they were limited by the manual computing ability. Okay, so how much can a man perform? How many computations a man can perform, right? So after that, when computers were introduced, people started writing codes for these numerical methods that were, that were solvable on the computers itself. So this is the era when actually a computer simulation was introduced, and this was nothing sort of a magic, right? Because the computers were solving everything that you wanted them to. But again, as the complexity of the problem increased, the the limiting factor was the size of the computers. So what do I mean by size? Size is essentially how complex operations can your computer solve. Okay, but then something known as parallel computation was introduced. I think most of you already know about it, and this played a major role in taking us a step forward in the field of computation. Then again, as humans are greedy, another problem was you have complex governing equations which involve multiple physics. You had crazy futuristic designs, and which is why, again, the simulations became a big problem. So I have personally seen some simulations run for 1 or 2 months together. So, imagine getting one result in 2 months of time from a simulation. So essentially, it was a computational hell. But then, this is probably the latest advancement, or maybe last to the latest. So people started using GPUs and co-processors for simulations, and this changed the game altogether. So from simulations that ranged in between, let's say 1 month or 1.5 months, the simulation time in some cases was reduced to maybe minutes or seconds. So yeah, that's right. So from months, you go to minutes and seconds. So imagine the kind of saving in time that you can achieve. Okay, so this we will talk about later, but that was the brief journey of CFD, or rather any numerical methods in history. So finally, the thing that you were all waiting for, we will now talk about CFD. So to put it simply, what is CFD? CFD is a branch of physics that utilizes advanced mathematical and numerical tools to solve complex fluid flow problems. Computational fluid dynamics, and hence I'm mentioning fluid flow problems. But CFD is not limited by just the fluid flow problems. CFD is very well used for a wide variety of applications, including combustion, your automobile application, space explorations, uh, fluid structure interactions. So what do I mean by that is your dam break problems, stuff like that. So CFD has a wide variety of applications, and obviously you will need multiple lifetimes to cover them all. Okay, but as a whole, right now we are going to look at CFD from a fluid flow perspective only. Okay, so there are essentially two aspects to understand CFD. One is the obvious is you install a CFD software, learn which buttons to click, and then just perform the CFD simulation. Oh, by the way, I've been using this word since quite a while. Everyone understands what's a simulation? Yes, no? I think you should know it from all the Hollywood movies that you watch. Perfect. Okay. So as I was saying, you have two approaches. One is, you just fire up the simulations using any of the CFD softwares by doing some sort of trainings in them. The other one is you actually understand what is happening behind the software. So the software essentially is a black box. You just interact with it from the outside, but what happens behind the software? What is the software actually doing during the simulation process? This is what I call as behind the scene mathematics. Okay, so I'm going to talk about both of them briefly, but I hope you follow it through. Okay, so to understand any CFD application, you need three things. First, you need to understand the physics of the problem that is involved. This physics of the problem is essentially conveyed using the governing equations that formulate this problem. So for example, this problem of ball falling from the top of the building that we were talking about, physics essentially is the gravity, and the governing equation you could say are the Newton's equation of motion. Okay, just to keep it simple. Okay, so this was one part. Second part is what we call as a numerical discretization. So this is a very big word, and sometimes it is very difficult to understand what it is. But to keep it simple, you can think about it this way. So let's say if you are, for example, going to Germany, okay, and if you want to interact people in Germany who don't know English, So essentially, whatever you have to say, you will have to translate it in German, right? Because only then the people will be able to interact with you. Similarly, if you want to pass on some information from the real world to CFD, then you will have to translate it in a language that CFD understands. Okay, or it can understand and solve it. So this translation process essentially is known as numerical discretization. Third is the solution algorithm. So for example, the Taylor series expansion that we did a while back. So whatever formula we had or whatever algorithm that was running, this is essentially the solution algorithm. Okay. So if we compare all of these three to, let's say, the Taylor series problem that we did, numerical discretization is, your complete domain that you had. So on the x-axis, we had values from 0, 1, 2, 3, 4, 5, and so on. So what you did is, if you want to evaluate the value at 2.1, you broke it down into 1, 1.1, 1.2. You started evaluating it one by one. And finally, you reach the value at 2.1. So what are you doing? You have a big scale from, let's say, 0 to 10. You started breaking it down into smaller parts. And finally, using all these smaller parts, you were able to evaluate the value wherever you wanted to. Okay. So this conversion process from breaking the big scale into smaller parts, this is known as discretization or numerical discretization in this case. Okay. So are these three terms clear to everyone? Take some 30 minutes, take some 30 seconds, spend some time whether you have understood it or not. If not, just let me know in the chat box. Okay. If there are any doubts, I'm here to answer them. If no doubts, feel free to type in a yes. Great. Thank you. Thank you for your feedback, guys. I'll still wait another 5 seconds. If anyone has any question, please drop it down. Okay, so governing equation, numerical discretization, and solution algorithms. These three terms are clear to everyone. So now, remember, we were talking about these from a behind the scene mathematics, meaning from the very core perspective. We nowhere talked about the software or how we are going to implement this from an application perspective and so on. Okay, this was purely the core CFD that is happening for any problem. Okay, now what we are going to do is we are going to talk about this from an application perspective. Okay, so just before we do that, since I mentioned governing equations, these are the equations which you should know when you're talking about CFD. Okay, so to those who already know about them, these are your Navier-Stokes equation, who are also known as the momentum equations. And then you have something known as a continuity equation, which is a mass conservation equation. Ideally, in a CFD course, this is where you begin with. But since this is a webinar and I don't want to, probably drown you into complex mathematics, let's just have a look at the terms in this equation and let's move forward. Okay. So the first term is known as a temporal term. Temporal meaning something that changes with respect to time. So U is the velocity, T is the time. So this is the temporal term. The second term is known as a convective term. So what is convective? Let's say if a fluid is flowing through a pipe, then one particle of the fluid is, pushing or taking with it another particle of fluid. So this is the convection. So this is what we call as the convective term. On the right hand side, you have the first term, which is your pressure term. So what is pressure term? Whenever you have a fluid flow, essentially it is happening because of some pressure difference. So that is being taken care of by this pressure term. And the last one is the diffusive term. So because you have your viscosity coefficient here, That is why it is known as a diffusive term. And lastly, you have this continuity equation, which is essentially the translation of mass cannot be created or destroyed. So if you consider a controlled volume, whatever changes in mass that happen, they all together add up to zero, because in all, mass cannot be created. That is what this equation says. Okay, so yeah, that is it from an equation perspective. Let us now deep dive here. Next, as I was mentioning, we are now going to talk about how CFD works, and this is where we talk about the application of CFD. Okay, so for example, let's say you download